Tzu-Yin Hsu. She is from National Tsinghua University. This talk is on-site contributed talk. So, Tzu-Yin, please start.
Okay. Hello everyone, my name is Tzu-Yin Hsu from National Tsinghua University. And today I want to talk about my recent research, which is about the molecular gas kinematics in one of the non-repeating FRB 18124B. And I was mainly working with Professor Hashimoto now. And my work is already published in MMRS this year. And this is my outline today. I will introduce briefly about fast radial bursts and then talk about the motivation of studying molecular gas kinematics, and then go into my paper's results, discussion, and conclusion, and end with my future plan of studying gas kinematics. So, fast radial bursts are millisecond duration radio transient with its brightness to Jansky level, and they are generally come from cosmological distance. And they are classified into two types. One is non-repeating FRBs, which doesn't repeat. Another is repeating FRBs. And actually, they are estimated that there are more than 1,000 FRBs on the sky every day. However, we have never known its origin. And this is a very big issue now in astronomy field. So, as we know, the problem is that we don't know the origin of FRBs now. So one of the things we can do is to constrain its physical environments of the host galaxies, and we can do many optical observations to the host galaxy too. And however, in this plot we can see that both non-repeating and repeating FRBs could be either star-forming or coalescing galaxies. So also there are diverse properties in the host galaxy too. So we don't have a conclusive answer in the optical data. So how can we get a hint of the origin of FRBs? That's a very big problem. So the solution is this work, which is to map the molecular gas kinematics in one of the non-repeating FRB hosts with ALMA telescope, which is in sub-millimeter wavelengths. So why are these molecular gas kinematics so important? Because molecular gas are the fuel of star formation. If we can know the molecular gas kinematics, we can investigate its physical environment, physical processes of the host galaxies, like smooth rotation, merger, or enfolding gas, etc. And that this may be a link to the birth of FRBs. And this is our target for this work, the host galaxy of one of the non-repeating FRB 18124B. It is a massive early type spiral galaxy with the redshift of 0.3216. So the FRB is here, a very tiny circle here. And this is the host galaxy region, the yellow circle. This is the optical image. And to investigate the molecular gas kinematics, we have to detect the CO emission line first. And this is the velocity integrated intensity map in the host galaxy region. The large red circle is the host galaxy region. And we can see that it is very bright in that region, and the CO emission line is significantly detected in that region. And we can extract the CO spectrum from this plot in the host galaxy region like this. The blue line here is the observed data, and the black line is the Best-fit Gaussian function. And there are two components there, which shows a asymmetric velocity profile. So this may indicate that if the gas is just smooth rotation, the two components there should be symmetric to the midpoint of 0. However, this spectrum doesn't show us to be symmetric, and instead of just showing the very asymmetric and weird spectrum. So we may infer that there is a disturbed kinetic structure of molecular gas in the host galaxy region. And to test whether this spectrum is really asymmetric, the spectrum, or the gas is really disturbed or turbulent in the host galaxy region, we can apply a asymmetric parameter, APIC. APIC is the peak ratio of the two velocity components there. This one and this one, the peak ratio. So the higher the APIC value is, the more asymmetric the spectrum is. and there may be more disturbed the gas is. And we also compare the AP value of our target with the H1 spectrum of the two repeaters, FRB repeaters host, these two FRBs, and the H1 spectrum is asymmetric of these two repeaters, and two gamma red burst hosts with its H1 spectrum is not asymmetric. So the AP value of our target, this one, is very high, higher than the two asymmetric H1 spectrums of the repeaters. So this means that the spectrum is really asymmetric, and there must be a disturbed kinetic structure of molecular gas in the host galaxy of our target. And we also plot the velocity structure of the host galaxy, like this plot in the right panel. And we can see that there is a smooth velocity gradient, range from negative 180 to 8 km per second. And we can see that there is missing positive symmetric components there. So this also shows a symmetric velocity gradient. And this may also indicate that there is a disturbed kinetic structure of molecular gas in the host galaxy of FRB 180124b. And we also plot the special distribution of the velocity components on the velocity integrated intensity map in the gray scale. And the first component is relatively close to the FRB position, and the second component, which is the red one, is relatively close to the host galaxy region. And this, in this plot, we can see that there are multiple special components there, and this may also infer that there is a disturbed kinetic structure of molecular gas in the host galaxy. So, in summary, there are a symmetric CO spectrum in the host galaxy and the asymmetric velocity gradient. And also, there is multiple special components in the velocity integrated intensity map in the previous slides. And we can infer that there is a disturbed kinetic structure of molecular gas in the host galaxy, one of the non-repeating FRB 180124b. And yeah, we also compare our results with the H1 detection of 3 repeating FRB hosts, the host galaxy of FRB 180916b, and FRB 181030a, and FRB 200120e, these 3 FRB hosts. So how about the gas kinematics? Do you think there will be smooth rotation or disturbed? How do you think? Okay. So for the first one, FRB 180116b, that is a velocity field of its host galaxy. You can see that, and there is negative components and positive components there, and there is a halo between these two components. And so we can infer that there is a merging H1 gas distance. And for another 2 FRB hosts, which shows H1 spectrums there, it's very obvious that there are very asymmetric profile in the H1 spectrums in these 2 FRB hosts. So we can indicate that there are all disturbed kinetic structure of H1 gas in these 3 FRB hosts. So, okay. So let's go to the conclusion part. The problem of FRB now is that we don't know the origin of fast radio bursts, and also we have no conclusive answers in optical data. We don't know what's the host galaxy classification. We cannot know what's the difference between non-repeating or repeating FRBs, or either we don't have a clear trend for that. So the solution of this problem, which is this work, is to provide another perspective to map the molecular gas kinematics in one of the non-repeating FRB 180124b host galaxies with AMA telescope, which is in sub-millimeter wavelengths. And the result is that we provide the first theo kinematics of the FRB host galaxy, and we found that there is a disturbed molecular gas structure in one of the non-repeating FRB's hosts. And also we found that there are similar H1 gas environments, which also shows disturbed gas structures in 3 repeating FRB hosts in these 2 papers. And therefore we can infer that there could be both non-repeating and repeating FRB host galaxies could have disturbed gas environments, and this can suggest a possible link between the gas kinematics and FRB progenitor. But you may think that this is not really, we don't have so much data, and yes, that's true. These four are the only gas detections of the FRB host. So now we want to do that is we want to have more molecular gas observations with ALMA telescope and in FRB host, and also more H1 observations to other host galaxies of FRBs with VOA or Green Bank and so on. And this is what I'm doing now too. Thank you very much. That's all.
Okay, thank you very much. We have 4 minutes for Q&A. So, is there any question from the on-site audience first? Or is there a question from online participants? Oh, okay, so there, from on-site.
Hello, Tzu-Yin. Thanks for your interesting presentation. Can you go to a preview?
This one?
Yes. I think my voice is large enough. It works. Do you mean in the further in the future, you are trying to use those telescopes to find the exact origin?
Actually, we cannot just say, oh, we can use this to say, oh, we can find the origin, but we can find the hints of the origin of fast radio burst.
Well, I have both thinking. I think machine learning can also help to find the exact origin. That's my comment.
Oh, thank you very much.
Okay, so thank you for the question. So, is there, okay, Shotaro, please. Online.
Yeah, thank you for a nice talk. My question is, so how did you choose this kind of target? Also, could you tell us more about what is your future plan? Which kind of observation you are going to combine? Which kind of data are you going to use? Could you tell me about this?
Okay. As for the first question, like I use the archival data, and I try to search all of the molecular gas detection of FRBs, and unfortunately there's only one is detection, so that's the reason why I choose this FRB as my target. And the second question is about the future plan. Yeah, like because if I want to do the molecular gas observations, one thing I need to get is I need the host galaxy's position and its properties. And actually, there are very few samples that is available for gas observation because it is a bit far, and we need to include the sensitivity of telescope. So actually, we are very limited. So we will choose the samples that can be observed to be our target. And yeah, we have proposals in VOA last cycle too.
Okay, maybe this could be related to Shivani's talk. She presented so many new discoveries, so maybe we can discuss this later in the discussion session.
Yes.
Thank you.
Thank you very much.
Okay, so thank you very much. We can use discussion time for the further questions to discuss. And then let's thank the speaker again. Let's move on to the next topic.